Permutations. A permutation, formally, is a bijection from a finite set S to itself. Right, so we've learned about bijections before. These are functions that are both injective, or one-to-one, and surjective, onto. And in other words, what that means is, in your domain and in your range, you're able to construct this correspondence between the two sets of elements that forms a perfect matching between the two. Right? So every element in the domain is mapped to exactly one element in the range, and everything in the range is also mapped exactly to one element in the domain. To give a concrete example, let's look at the set S, which contains the four elements A, B, C, and D. Right, so one example of a bijection is we can map A to B, B to D, C to C, and then D to A. Right, so again, it's easy to check. It's one-to-one, it's onto, therefore it's a bijection. And this is an example of a permutation, right? Because your domain here is S, and it's a bijection from S to itself. We can also represent this specific permutation by the string B, D, C, A, or from left to right, just B, D, C, A, to represent the image of each element in the domain, where we take a specified order for these elements, right? So essentially saying the first position is what A maps to, the second position is what B maps to, and so on. Right, so there are other permutations as well on the same set, right? A, B, C, D is also a permutation. It's the bijection that maps each element in the domain to the same element. D, C, B, A is another example, and there are many others. And so the question we're asking here is, how many are there? Right? How many permutations are there how many permutations are there on the set S? And so this is now a counting problem, right? We have a set S, we know what permutations are. How do we count the number of permutations? Well, let's think about using the product rule here, right? What we did to construct this permutation at the beginning, BDCA, was to basically pick an element for each of A, B, C, and D, one after the other. Right? So we're kind of doing an operation step by step here. And so let's count the number of choices we have for each step. For the element A in the domain, how many choices do we have in the codomain? Well, we have 4 choices at this point, right? We can map it to A, B, C, or D. So there are 4 choices here. So let's suppose we map it to B, right? So that's what we did in our example permutation. How about B? Well, now that we've mapped A to B in the first step, in the second step, well, regardless of where you mapped A to, you'll have 3 choices left for B. Right, so let's say we're mapping B to the element D. And you should see where this is going now. Now you only have 2 choices left for C, because you've already mapped A and B on the left to B and D on the right. Right, so for C, you can only map it to A and C. We choose C. And finally, when we get to the last element here, well, we have no choice but to map it to A. Right, so I'll write that in blue here, A. So what this means with the product rule is, well, you just have to multiply the number of ways you can do each of these successive operations together to get the total number of ways to perform the whole operation. Right, so the answer here is, by the product rule, there are 4 times 3 times 2 times 1, which is 24 of these permutations. Now, if you think about the more general problem of how many permutations are there on a set of size n, right? So suppose S contained the numbers from 1 to n. How many are there? Well, you can already see what the pattern is here. You're just going to be multiplying n by n minus 1, by n minus 2, and so on until 2 and then 1 to count the number of ways to form a string of length n using the elements from 1 to n. And, well, we know this is the factorial, right? And so by the product rule, there are exactly n factorial permutations on a set of size n, or n factorial bijections from a set of size n to itself, or equivalently n factorial ways to arrange n distinct objects in a row, which you can see here, and also n rearrangements of a word with n distinct letters. Now let's just work on one example. Let's look at this one. How many words can be formed using the letters of the word equation? From the previous slide, we know that we only need to count the number of letters in the word. And so there are 1, 2, 3, 4, 5, 6, 7, 8. Therefore, there are 8 factorial rearrangements. Right? Now you do have to check that these letters are all distinct. Now what happens if some of the letters were the same letters? Well, we'll get to that in another topic. Look at this next example. How many 3-letter words can be formed using the letters of the word equation? So it's the same word. There are 8 distinct letters here. But now you're not rearranging all the letters to get a word of the same length. Right? We're only looking for 3-letter words here. So to give you some examples, we can pick E, Q, U, the first 3 letters of the word. We can pick I, O, N, the last 3 letters. And A, E, I, A, O, and so on. And so it's not going to be simply 8 factorial here, right? Because if you look at the operation that you're performing, well, there are only 3 steps to it. Step 1, the first letter of the 3-letter word we're forming, how many choices do we have for it? Well, we have 8 choices. Right? So say you pick E for the first spot. That leaves us with 7 choices for the second spot. Say you pick Q. You've already picked E, right? So you can't repeat E anymore. That's why the number of choices go down. And then finally, you have 6 choices for the third spot there. And 8 times 7 times 6 is the answer here, which is 336 possible 3-letter words. Right? And again, that's just the product rule in action here, right? You have an operation and you know what steps you have to take in order to complete that operation. You just count the number of ways to perform each step and you get the total. We also call this a permutation of 8 things, or I mean, let's call them objects, of 8 objects, taken 3 at a time. Right? Because you're still permuting them, you're still rearranging them, but you're not taking all of them anymore. You're only taking 3 at a time and looking at these smaller rearrangements that you get. And so the question I'd like to leave you with in this video is, well, can you generalize this to count the number of permutations of n distinct things taken k at a time? In other words, how many k letter words can be formed using a word with n distinct letters?